In this lecture, we're going to discuss rational functions with a focus on vertical and horizontal asymptotes and finding holes in the graph. Let's formally define what a rational function is. A function f is a rational function if f of x equals g of x divided by h of x, where g of x and h of x are polynomials. So a rational function is just the quotient of two polynomials. Because the numerator is a polynomial, you'll be able to plug any number you want into that. The denominator is also a polynomial, but you can't divide by 0. So the domain of the function is the set of all real numbers except for the zeros of the denominator, what we're calling h of x. When you run into one of those domain restrictions, something weird has to happen in the graph. There can't be a point at that spot. And there are two possible things that could happen there. You'll either get a vertical asymptote at that location, or there'll be a hole in the graph. If there's a vertical asymptote, the function has a very specific behavior. At an asymptote, the function's behavior is either to shoot up towards infinity or shoot down towards negative infinity. Here are a couple of examples of graphs that have vertical asymptotes. In the graph on the left, you can see that the function is tending towards infinity as we get closer and closer to 3 from the left side, and that it's shooting down towards negative infinity as we approach 3 from the right side. When we draw graphs by hand, we often use some sort of dashed line to indicate where the asymptote is. Drawing that dashed line in there just makes it clear where the domain restriction is. We draw a dashed line to indicate that that's not part of the graph. It's some sort of reference line for the graph. So in this example, the vertical asymptote is the line x equals 3. We can use that arrow notation to describe what's going on. As x approaches 3 from the left, on the left side of 3, the y-coordinates are going towards infinity. As x approaches 3 from the right side, the y-coordinates are going to negative infinity. In this second example, we only see the behavior on one side. Again, drawing the graph without the dashed line makes this a little bit ambiguous. It's hard to tell whether I mean for this graph to slowly keep slanting forever to the left, or if it's leveling off at this spot. So I draw in the dashed line to try to make that a little clearer to the reader. Now I see that the intention was for the function to kind of shoot down towards negative infinity as we get closer and closer to this input x equals negative 1. So here the line x equals negative 1 is the vertical asymptote. We will commonly abbreviate vertical asymptote VA. And here we can only talk about the behavior on one side because we only see one side of the graph. As x approaches negative 1 from the right, the behavior of this graph is to shoot down towards negative infinity. The y-coordinates are getting smaller and smaller with no bound. So visually we see what a vertical asymptote is. How do you determine where the vertical asymptotes are if you don't have the graph in front of you? Here's a rule. If f of x equals g of x over h of x is a rational function in lowest terms, where you've reduced it as far as you can, and h of a is equal to 0, but g of a is not equal to 0, so the denominator is 0 but the numerator isn't, then x equals a is a vertical asymptote of the graph of y equals f of x. So if you've got a rational function reduced as far as you possibly can, and there's a number that makes the denominator 0 without making the numerator 0, then there's guaranteed to be a vertical asymptote at that location. Here's a simple example of determining where a vertical asymptote is. Find the vertical asymptote, or asymptotes, we'll pretend like we don't know how many there are, of f of x equals 1 over x minus 3. You can see this function is already in lowest terms, there's no way to reduce this. Is there any input that makes the denominator 0 without making the numerator 0? Sure, x equals 3. X equals 3 is not in the domain of this function. Notice that plugging 3 in does not make the numerator 0, it only makes the denominator 0. So the vertical asymptote is the line x equals 3. Let me show you in the calculator what this graph looks like so we can verify that. 1 divided by, I have to make sure that I put all of x minus 3 in the denominator, so I need parentheses. X minus 3. I'm going to graph that on the standard window. And you'll notice that the function kind of freaks out right at x equals 3. It shoots down towards negative infinity on the left side and up towards positive infinity on the right side. You can see visually that this function really does seem to have an asymptote at x equals 3. There had to be some sort of weird behavior because 3 isn't an allowable input. And one of the possibilities is that you've got a vertical asymptote. I've got a harder one I'd like you to try. Find the vertical asymptote or asymptotes of the function f of x equals 2x plus 1 over x squared minus 7x minus 18. To find the vertical asymptotes, we need to know that the function is in lowest terms. So the first thing I'm going to do is factor that denominator. The numerator doesn't factor in any meaningful way, but the denominator factors to x plus 2x minus 9. I see that nothing cancels, so f of x is in lowest terms. Now I look to see if there are any numbers that will make the denominator 0 without making the numerator 0, and there are in fact 2 of them. Negative 2 makes the denominator 0, and positive 9 makes the denominator 0. This function has 2 vertical asymptotes. Quick nerd point about how we write our answers. It's important that you write the vertical asymptotes as equations. X equals negative 2, x equals 9. These are equations of lines. They're not solutions to an equation. So you can't say the vertical asymptote is negative 2. Negative 2 isn't a line. Negative 2 is a number. But x equals negative 2 is a vertical line. X equals 9 is a vertical line. So make sure you write those as equations. Equations of vertical lines. Again, I want to show you that we're not lying here. Let me graph this in the calculator. Here we have to put the numerator and the denominator in parentheses. When we graph this, we see that the function kind of freaks out in 2 spots. There's this spot right here, which appears to be around negative 2, and there's this spot way over here, which appears to be at 9. This time it's kind of harder to see, especially at negative 2. So let me show you how we can verify that there's at least something funny going on at negative 2. If we try to trace the function to the spot where x equals negative 2, you'll notice that the calculator leaves the y blank. That's because there is no output at negative 2. Negative 2 is not in the domain of the function. And based on the calculator's graph, it appears that the function is shooting down forever on one side, it's shooting up forever on the other side. That's an indication of a vertical asymptote. The spot at 9 seems a little bit clearer, but we can verify that as well by typing 9 and hitting enter, and we see that there really is a vertical asymptote at 9 as well. You'll notice we ignored the numerator in finding the vertical asymptote. It's okay to get 0 in the numerator. When the numerator comes out to 0, that's just going to be an x-intercept of the graph. It's where the y-coordinate of the graph is going to be 0. In this example, that happens at negative 1/2. Let me pull the calculator back up. It's hard to see it, but at negative 1/2, the function's passing through the axis. That's how it gets down here. I can trace that as well. If I trace this to negative 1/2, negative 0.5, you can see that the y-coordinate is 0. That's not an asymptote, that's just a point on the axis. So when we were first describing what vertical asymptotes are, we used arrow notation to describe the behavior on each side of the asymptote. Let's talk about how you can do that without looking at the graph. Use arrow notation to describe the behavior of f of x equals 1 over x minus 3 on each side of the line x equals 3. This is the same as this example, and we determined that there was a vertical asymptote at x equals 3, and now we're going to describe the behavior on each side. So we're going to say, as x goes to 3 from the left, f of x has some behavior, and as x goes to 3 from the right, f of x has some behavior. And there are only 2 possible answers here. The function is either going to go to infinity or negative infinity. So how do we determine that? Well, I guess we could cheat and graph it in the calculator. We have already looked at what the graph looks like. But how can we do it using intuition? All you got to do is consider the type of input you're plugging in. If we're approaching 3 from the left, that means we're plugging in a number that's smaller than 3. If you plug a number that's smaller than 3 into the denominator, you're going to get a negative result. The numerator is positive and the denominator is negative. That's always going to be a negative quotient. So as we get closer and closer to the asymptote, those negative quotients are going to approach negative infinity. It can't go to positive infinity because every input smaller than 3 is going to make the denominator negative. The numerator is positive, the denominator is negative, that quotient is going to be negative all the time. If we approach 3 from the right, then we're considering numbers that are bigger than 3. When the input is bigger than 3, the denominator will be positive. We've got a positive numerator, we'll have a positive denominator. These must be tending towards infinity. Just to show you that our intuition is right, let me pull the graph back up. As we approach 3 from the left, the graph is tending down towards negative infinity, just like we said. As x approaches 3 from the right, the graph is tending up towards positive infinity, just like we said. We're able to figure that out using intuition because of the sign of the numerator and the denominator. We know that the function's either going to infinity or negative infinity. We just have to know whether the quotients are positive or negative in order to determine that. We can also investigate this numerically. We can just plug some numbers in for x and see what happens as we get closer and closer to 3 on each side. I'm going to do this using the table. If you have questions about using the table, just contact me. I'll show you how to do this. I'm going to plug numbers in for x and get the corresponding output for y. So let me plug in 2 first. Now we don't need a calculator to plug in 2. 1 over 2 minus 3 is 1 over negative 1. That should come out to negative 1. But now I'm going to get progressively closer to 3. So I'll plug in 2.9. That goes to negative 10. Then 2.99. Negative 100. 2.999. Negative 1,000. I think you're probably convinced. I'll keep doing it. But you can see that the outputs are getting smaller and smaller and smaller without bound. As we get closer and closer to 3, the outputs get progressively smaller. 10 times smaller for each 9 that I've added with these examples. And so you get the feel that this function really is tending towards negative infinity. We said as x approaches 3 from the right, the outputs approach infinity. Let's investigate that as well. Let me start with a number bigger than 3. Let's start with 4. We don't need a calculator for 4. That's 1 over 4 minus 3. That's 1 over 1, which is 1. Nice. Now we'll get closer and closer to 3 on the right side. So we'll start with 3.1. And then 3.01. And then 3.001. And you can see it's the same story. The outputs are getting larger and larger without bound. As I get closer and closer to 3, the outputs get bigger and bigger and bigger, and they tend towards infinity. Both the investigation with the graph, which was practically cheating, and the numerical investigation using the table verify our intuition that we used here. So again, a vertical asymptote is just one of the possible consequences of a domain restriction in a rational function. The other possibility is that there's a hole in the graph. If f of x equals g of x over h of x is a rational function where g of a and h of a are equal to 0, then the function can be reduced by a factor of x minus a. This goes back to what we were talking about in previous sections. If a is a 0 of a polynomial, then x minus a is a factor. So that means that x minus a would be a factor of the numerator, and x minus a would be a factor of the denominator, and we can cancel. So you can reduce. If after you reduce, a is an allowable input to that reduced expression, then the function doesn't have a vertical asymptote. Instead, it has a hole in the graph at the point where x equals a. The function's behavior won't be to tend towards infinity or negative infinity. It will tend towards what you get when you plug a into the reduced version. Let me show you what I mean. I'm telling you in advance that the graph of f of x equals 3x minus 6 over x squared minus 4 has a hole in it. We're going to determine the location of that hole. In order to determine the domain restrictions of this function, we need to get the denominator factored. So let me factor the denominator. So this function has 2 domain restrictions, negative 2 and positive 2. But does that mean that there are 2 vertical asymptotes? Well, if I plug negative 2 into the numerator, I get negative 6 minus 6, that's negative 12. And negative 12 over 0 is an indication of a vertical asymptote. But if I plug 2 into the numerator, I get 0 in the numerator as well. That means that we'll be able to cancel a factor from the numerator and denominator. Some of you probably noticed that the numerator factored as well, and you might wonder why I didn't factor it right away. Well, I wanted to make the point that this doesn't necessarily correspond to 2 vertical asymptotes because we haven't made sure that the function was in lowest terms. So when I cancel these factors of x minus 2, I get that this is equal to 3 over x plus 2, assuming that x is not equal to 2. You can see that this function is going to have a vertical asymptote of x equals negative 2, but what happens at 2? At 2, there's a hole in the graph. There won't be an asymptote because what is the behavior of the reduced version when x is close to 2? Well, the output will be close to 3/4. In fact, that's how you determine what the y-coordinate of the hole is. You plug this number that you're not allowed to plug into the original function into the reduced version and see what you get. We would get a y-coordinate of 3/4. So the hole is at the point 2, 3/4. There will not be a vertical asymptote at x equals 2. Let me show you. If I graph this on the standard window, you'll see an asymptote on the left side at x equals -2, but there's no asymptote at x equals 2, and that's because there isn't an asymptote, there's a hole in the graph. Now the calculator doesn't do a good job of showing that hole, but I can verify that there's a hole in the graph by tracing it to x equals 2. You'll notice that it doesn't give me an output. It's hard to tell where the hole is at x equals 2. The calculator won't tell us because there's a hole in the graph. It turns out that the y-coordinate is at 3/4. That seems reasonable based on where the graph is sitting at x equals 2. It's somewhere below 1. So there is a vertical asymptote at x equals -2, and that's because even after we reduced, -2 made the denominator 0 without making the numerator 0. X equals 2 made both the numerator and denominator 0, and when we reduced, we were allowed to plug 2 into the function. That's an indication of a hole in the graph. The number that you weren't allowed to plug into the function is the x-coordinate of the hole, and to get the y-coordinate of the hole, you just plug that x-coordinate into your reduced version. The other topic we're going to cover in this video is horizontal asymptotes. What is a horizontal asymptote? Well, we say that the line y equals c is a horizontal asymptote for the graph of a function f if f of x approaches some number c as x goes to infinity or as x goes to -infinity. So a horizontal asymptote indicates something about end behavior, but unlike the end behavior of a polynomial that shoots to infinity or -infinity, here we're saying that the behavior is to level off at some number, and we call that a horizontal asymptote. So here are a couple of graphs with horizontal asymptotes. In the first graph, it looks like the function is leveling off at y-coordinates of 3 on both sides, and just like with vertical asymptotes, we often use dashes to indicate this. I usually only put those dashes on the ends to indicate that this is an end behavior issue. A lot of people will draw them all the way through, and that's fine. There's nothing wrong with that. But to emphasize that horizontal asymptotes are an end behavior issue, I like to use the dashes just on the ends. So here the horizontal asymptote is the line y equals 3. As using our arrow notation, we would say as x goes to -infinity, y goes to 3, and as x goes to infinity, y goes to 3. In the second example, that only happens on one side. It levels off right at the x-axis. The x-axis is the line y equals 0. The end behavior here is as x goes to -infinity, y goes to 0, and that's why y equals 0 is a horizontal asymptote. It turns out that if a rational function has a horizontal asymptote, there's a pretty simple rule for determining what it is. It's going to look complicated at first, but the rules aren't that bad. Let f of x equal g of x over h of x be a rational function, so g and h are both polynomials. Therefore, they both have a highest power. If the degree of g of x is less than the degree of h of x, then the line y equals 0 is the horizontal asymptote of the graph of f. If the highest power on top is smaller than the highest power on the bottom, then the function is going to level off at the x-axis on both sides. The next rule is very wordy, but the idea is simple. If the degree of g of x is equal to the degree of h of x, so the highest power on top and bottom are the same, then the horizontal asymptote of the graph of f is the line y equals c over d, where c is the leading coefficient of g of x and d is the leading coefficient of h of x. So if the numerator and denominator have the same power, we just take the ratio of their leading coefficients. Let's start with an example like that because the rule seems complicated, but it's not that bad. Let's find the horizontal asymptote of the graph of f of x equals 6x plus 1 over 2x minus 3. To find the horizontal asymptote, I compare the degree of the numerator to the degree of the denominator. Both the numerator and denominator are first degree polynomials. Highest power of x in the numerator is 1, the highest power of x in the denominator is 1. According to the rule, if the degree of g of x is equal to the degree of h of x, then the horizontal asymptote of the graph of f is the line y equals c over d, where c is the leading coefficient of g of x and d is the leading coefficient of h of x. The horizontal asymptote is found by just taking the ratio of the leading coefficients. So I take 6 divided by 2, which actually simplifies here, that's 3. So the line y equals 3 is the horizontal asymptote, which we're going to denote by HA. This function is going to level off at y equals 3. Now I want to verify this by showing you in the calculator. I've typed the function into y1, parentheses around the numerator and denominator because they're both binomials. And when I hit graph, you can see that the function levels off, and it's hard to tell exactly where, but it appears to be at 3. And here's one way to see that. I'm going to hit the trace key, and it gives me the cursor in the center of the screen. And instead of typing in numbers, you can actually use your arrows to follow the curve. So I'm going to keep scrolling to the left. Watch those y coordinates as I scroll further and further to the left. You'll notice that they're increasing, but they're starting to level off as I go further and further to the left. And you can't tell exactly, but it does appear that they're honing in on 3. A better way to do this might be to use the table. Let me pull up the table. And I'm just going to start plugging in numbers that are getting progressively larger, letting x go to infinity. So I'll start at 10, then I'll plug in 100, then I'll plug in 1,000. And you notice that as the input gets larger and larger, the output's getting closer and closer to 3. That would also happen with negative inputs. This is what we were investigating in the graph. If I start with, say, negative 10, and then go to negative 100, and then negative 1,000, and I don't have to do powers of 10 like this. Let me do negative 16,384, some weird number. You'll notice that these outputs are getting closer and closer to 3. The function is leveling off at y equals 3. You can see it in the graph, kinda. It's hard to tell that it's exactly at 3, but then a numerical investigation gives that away. So y equals 3 is the horizontal asymptote. As an aside, you see how the function's breaking right here? That's because of the domain restriction at 3/2. The vertical asymptote is the line x equals 3/2 or x equals 1.5. That wasn't a question in this example, but I hope you can see that that's what's happening there. Now, why does it work this way? Why can we just take the ratio of the leading coefficients? Well, the idea is as follows. Because we're letting x get very large in size, these constant terms aren't really going to matter. When x is really big, the plus 1 is going to say nothing. Like suppose you plug a billion in for x. Adding 1 to 6 times a billion has almost no effect. Same thing in the denominator. If we're plugging some obnoxiously large number in for x, subtracting 3 is going to have practically no effect. So when x is really big, those last two terms are negligible. And you're basically just getting 6x divided by 2x. Not exactly, because there really are other numbers there. That's why none of those answers in the calculator were coming out to exactly 3 in the table. When I pull up the table, I'm not going to ever get exactly 3, but I'm going to get closer and closer to 3 because the plus 1 and the minus 3 have less and less effect as x grows in size. So for all practical purposes, this might as well be 6x divided by 2x. Well, those x's cancel, and you get 6 divided by 2, which is 3. And that's why the rule works the way it does. Let's look at an example that uses the other rule for horizontal asymptotes. Let's find the horizontal asymptote of the graph of f of x equals 3x plus 1 over x squared plus 2. Let's go back to our rule. If the degree of the numerator is less than the degree of the denominator, then y equals 0 is the horizontal asymptote of the graph automatically. That's exactly what happened here. We don't need to do any work. The line y equals 0 is the horizontal asymptote. Notice again that I'm writing my answer as an equation because I need the equation of a line. You can't just say 0 is the horizontal asymptote. 0 isn't a line. It's the line y equals 0. Let me show you this in the calculator. So I've typed in the function again. Notice the parentheses. I'm going to graph this function on the standard window. And this function looks a little bit different. It doesn't look like any of the other graphs we've had so far. I'll explain why in a moment. Notice that it levels off at the x-axis on the right side. It also levels off at the x-axis on the left side. And what is the equation of the x-axis? That's the line where all of the y-coordinates are 0. So that's the line y equals 0. Now why does this graph look so much different than the other ones that we've looked at? It doesn't have any vertical asymptotes. Look back at that function. The denominator is x squared plus 2. X squared plus 2 has no real solutions. There aren't any domain restrictions here. Because there aren't any domain restrictions, you're not going to get any vertical asymptotes, and that means that the graph's going to look a little bit different than some of the other ones we've looked at. Why does it make sense that the horizontal asymptote is going to be y equals 0? Well, when we plug obnoxiously large numbers in for x, in the numerator we're just multiplying by 3. And yeah, there we're adding 1, but the 1 practically doesn't matter. In the denominator, we're squaring that obnoxious number. So when we plug in like a trillion, in the numerator it's 3 times a trillion, but in the denominator it's a trillion times a trillion. When we plug in really big numbers, the denominator is going to be way bigger than the numerator. And when the denominator of a fraction is way bigger than the numerator, the fraction's value is really close to 0. Again, let's investigate this numerically. Let me pull up the table. And you can see it here already with the numbers I've plugged in. As the inputs get progressively smaller without bound, the outputs get smaller and smaller. That last one looks big, but it's actually in scientific notation. So that's like negative 0.00018. These are getting really, really close to 0. Let me do the same thing on the positive side. So I plugged in some powers of 10 here. You can see that these outputs are getting closer and closer to 0, where this last one is in scientific notation. That's like 0.0003. The line y equals 0 is the horizontal asymptote. Before we recap what we've learned here, let me point one thing out. In my rule for horizontal asymptotes of rational functions, I described what you do when the degree of the numerator is less than the degree of the denominator, and I described what you do when the degree of the numerator is equal to the degree of the denominator, but I didn't give a rule for what happens when the power on top is bigger than the power on the bottom. And that's because you don't get a horizontal asymptote in that case. You get what we call an oblique asymptote, and we'll cover that in a future lecture. For now, I just want to recap these horizontal and vertical asymptotes with a couple of examples. This says find all asymptotes of the graph of f of x equals 2x squared plus 4x over 3x squared minus 5x minus 2. We're going to start with the horizontal asymptote because it's actually the easier one. The horizontal asymptote is found by first comparing the degree of the numerator and denominator. Well, they have the same degree. They're both second degree. And then following the rule. When the degrees are the same, you take the ratio of the leading coefficients. The leading coefficient of the numerator is 2. The leading coefficient of the denominator is 3. The ratio of the leading coefficients is 2/3. So the horizontal asymptote is the line y equals 2/3. As x goes to negative infinity, the function will level off at y equals 2/3. As x goes to infinity, the function will level off at y equals 2/3. To find the vertical asymptotes, we're going to need this factored, and we want to factor both the numerator and the denominator because we want to make sure we don't fall into the trap of listing a whole as an asymptote. So to factor the numerator, I pull out a 2x, and it leaves behind a factor of x plus 2. In the denominator, 3x times x to get 3x squared. 1 times 2, let's see, this is 2 and this is 1. And this is minus 2 and plus 1. So these don't cancel. That's important. That means that both domain restrictions will give us vertical asymptotes. There are two vertical asymptotes. The line x equals negative 1/3, that comes from setting this equal to 0 and solving for x. And the line x equals 2. Comes from setting this equal to 0 and solving for x. That's easier to see. You get vertical asymptotes when the denominator is 0 but the numerator isn't. I've got one for you to try. Find all asymptotes of the graph of f of x equals x minus 3 over 4x squared minus 12x. The horizontal asymptote is the easier one. The degree of the numerator is smaller than the degree of the denominator, so that's automatically the line y equals 0. To look for vertical asymptotes, we need to get the denominator factored. So we can pull out a 4x and it leaves behind an x minus 3. And 0 makes the denominator 0, so one of the vertical asymptotes is x equals 0. And 3 also makes the denominator 0, but is that a vertical asymptote? No, because we can cancel that factor away. This reduces to 1 over 4x. The question doesn't ask this, but there's a hole at x equals 3. If we wanted to figure out the y-coordinate of the hole, we just plug 3 into the reduced version. X equals 0 is a vertical asymptote because even in the reduced version, 0 makes the denominator 0. So we've defined what a rational function is, and we've determined the rules for finding the vertical asymptotes, the horizontal asymptotes, and the holes in the graph. If you have questions about any of these topics, please don't be afraid to reach out to me. You can come see me in an office hour, or you can shoot me an email.